Hello, everybody, and welcome back to the Math and Physics Podcast. I am your host, Parker.
And I'm Ray, and we welcome you to episode 22, where today, right?
Nope.
Wait, isn't it 22?
No, it's not.
Wait, is it 21? No, it's 20.
No, it's 23.
Oh, it's 23. Oh, it's 23. I'm so sorry. I apologize.
Yeah.
Welcome to episode 23, where today we're going to be talking about parallel universes, timelines, multiverses, and a little bit of quantum mechanics too.
You betcha.
This is going to be a fun podcast.
And everybody get excited for possibly next episode. We're going to have a guest.
Are you letting them know?
No, I'm not. I'm going to keep it a surprise.
Okay. Smart.
But there's going to be a very nice guest that's going to come on, and I'm pretty sure if you're into math and you're into physics,
you will know him.
You probably know who this guy is. So yeah, we're very excited to have him on, and it's going to come soon. If it's not the next episode that we have our guest, then next episode we're going to start a new series called History of Physics.
Ooh.
Where each of us we're both going to pick one physicist or a mathematician, and then we're gonna educate you guys on what they did and how they contributed.
I like this idea.
Yeah, how they contributed to the math physics world, and what resulted from their discoveries, etc.
Okay, that sounds fun. We can do a physicist each. Yeah, sounds dope.
Yeah.
Sounds awesome.
Yeah, and hopefully, by the time we get to part 6 of History of Physics, we have kind of a good overview of, most physics / math / astronomy. We can do Copernicus, etc. There's a lot of people we can cover.
Yep. Yeah, I mean, we have kind of unlimited time right now, so, we can just keep covering more and more people. Let's see where it goes.
That's right.
Okay.
Yeah, getting into today's podcast, we were talking about parallel universes. So, it's kind of in the name. Auto-descriptatory. It's
what?
It's a
what?
Auto-descriptive.
Oh, it describes itself, is what you're trying to say?
Yes.
Yeah, okay.
It's a universe. Well, technically it's a set of universes that follow each other in parallel. So they don't cross each other, but they just exist separately.
Mm-hmm.
And so in theory, there are an infinite amount of parallel universes where an infinite amount of events occur. So there's one universe where Ray and I are doing this exact podcast, except right now at this second, I say cat instead of dog. And then there's another universe where I say them in the opposite order. And,
basically,
that's just the idea of how, with an infinite amount of universes, just the exact same thing can happen in two universes, except, one particle is in a different location. And other than that, everything is the exact same.
Yep.
Which is pretty cool to think about.
The real question in all this really is, how did this even come to be? How did we even think of, a universe where everything is parallel to each other? Because we've had the idea of multiverses, right? Where, they're just different universes, just in general. But now we're starting to introduce these things called parallel universes that are not, they technically do exist in a multiverse, but they're, as Parker said, basically parallel representations of each other, with just small fluctuations between each universe. So how does it really happen, right? So it all began, I think this began with the quantum mechanics interpretation, with the two biggest interpretations in quantum mechanics. So this basically depends completely on how you view quantum mechanics. One is known as the Copenhagen interpretation, which is what we're so used to. And the other, which is where parallel universes come from, is known as the many worlds theory. So the Copenhagen interpretation is, for example, when we discuss probability. So this particle has a 50% probability being here, 30 being here, 20 being there, right? That is Copenhagen interpretation of quantum mechanics. That's what we've been brought up with, and that's probably what we're going to be doing in grad school and just throughout our entire lives, because that's basically the interpretation that we take right now. The many worlds, on the other hand, you remember Schrodinger's cat, right? That it's dead or alive?
Mhm.
So the Copenhagen interpretation says that it can be both at the same time, right? Dead and alive. The many worlds theory, however, says that there is literally going to be a split in universes that creates these two parallel universes, where in one universe the cat is alive, and in the other it is dead. So the entire idea of parallel universes came from a simple interpretation of quantum mechanics. And I think that's pretty cool. I think that's really cool.
Yeah, so going back to the Copenhagen interpretation, so the term actually comes from back in the 1920s when Niels Bohr and his assistant Werner Heisenberg, they were, originating the quantum mechanical theory at the time, and they were both operating out of Niels Bohr, his institute in Copenhagen. So that's why it's called the Copenhagen interpretation.
I just think in general, this is a really cool way of looking at quantum mechanics in like two different ways. Because we've always looked at it as a probability, right? Like every time. Our entire first year was built on the premise that these particles have probabilities of being in different places, right? But this can all just be a theory for all we know, to be honest. I mean, we do have proof of this, right? Do we?
Proof of what?
Like, do we have proof of that particles are in fact in a probability? There is proof of that, isn't
there? Well, yeah, obviously.
Yeah.
That's what.
Yeah, I mean,
that's what quantum mechanics is based off of.
So then, I guess many worlds are just another theory that you can always just, it's always just there. There's no real way to disprove it.
It's not just a theory. It's called like the many worlds interpretation.
It's more of like yeah.
Because quantum mechanics is like it's its own domain, and the way you can take the information and filter it is through different interpretations, right? So they're both correct in their own different lanes, I guess.
Yes, sir.
One thing that I was thinking about is that with the many worlds interpretation, what you can kind of apply to, think about what's it called? What was like the smallest unit of time?
Planck time.
Yeah. Imagine every single Planck time, you have the decision at any moment to do one thing or another, or to not do anything at all, right? So imagine that at every single Planck time, where you like direct your hands or your feet or your thoughts or whatever, every single instant, there's a chance that it diverges from another. So think about the amount of parallel universes that can emerge.
I know that
from that, right?
That is insane.
Right, because when you go down to the fundamental level, your atoms could be in a different position versus if you would have, stuck your hand in the air. So every single Planck time, there could be a variance between the decisions that you make and how that influences, where you are and what happens in the future.
It's crazy that like such a small decision or such a small like observation, a measurement can just completely, or in the many worlds theory at least, interpretation, I mean, completely split apart universes and create two parallel universes. I think that's just insane. But one big thing about the difference between the Copenhagen interpretation and the many worlds interpretation is the wave function collapse, right?
Yeah.
So in the Copenhagen interpretation, we take the wave function to collapse when we measure the object, right? But in the many worlds interpretation, this is where it gets interesting. Because it's many worlds, what they say is that the observer and the object you're observing are both in multiple states at the same time. So your current state gets entangled with the current state of the object you're observing. So in an opposite world or a parallel world, you would have observed something opposite. But in this world, you observe something else. Hence, the wave function doesn't collapse because both things are being observed and everything is being measured. So they kind of view it in two different ways, with one being collapsed and one not. So that's a big difference between them. Just
Yeah, so technically, instead of just like before you observe it, there's a probability, and then after you observe it, it's just
Bang,
know
right there.
you know its position
Yeah.
or its momentum. With the MWI, many worlds interpretation, basically the wave function doesn't collapse, and so everything just still happens. Like everything exists, but exists on another timeline.
Exactly. Like every probability that electron had to be observed will exist in another timeline is basically what the outcome of the many worlds interpretation is. I mean, it's just a different way of doing it.
It's a lot simpler to think about when with the Schrodinger's cat, because there's only two options. It's either the cat is dead or the cat is alive.
Yeah.
But as long as you don't check, right? As long as you don't check, the reason we say that the cat is dead and alive at the same time is because, let's say, like, the timeline of the cat, it's not split into two, but it's both at the same time. So they're kind of one on top of each other. And then once the observer checks, basically, at that point, the two timelines separate, and then you get entangled with both timelines, but the one that you're existing in gets entangled with the one that you observe. Yeah.
And the interesting thing about all of this is that you technically, or you, in this case the cat, has no idea that there is a whole new universe created with the same cat where there is a different outcome. So in this universe, the cat could be dead, and I mean, it wouldn't even know that it is actually alive in another universe. That's the thing, like it's, but then this is kind of, this entire concept though, is what introduces like so many big philosophical questions, right? Because the problem with the parallel universe theory is that now you have multiple, almost infinite versions of yourself. So if that is possible, which one, philosophically speaking, is truly you? And all of those questions come up, and then even philosophers can go into this in a whole new way. I think it would be really interesting to search up the philosophy of the many world interpretation. It's really cool.
I was actually right about to say that.
Yeah.
I was going to say there's a point in which like quantum mechanics really just borders the line between science and philosophy, because you hear something like, what we're talking about right now. You hear that and you're like, how is that even true? Like, this is just like you see symbols on a piece of paper and you go, yeah, there's an infinite amount of realities, and it kind of sounds like we're just making things up based on symbols and equations.
But again, if you think about it, there's no real way to prove the many world interpretation, is there?
Well,
I'm pretty sure there is.
I don't think so.
But if I'm not mistaken, before Stephen Hawking died, right? He released this paper that unfortunately I don't believe was successful because he hadn't finished it. But it was something where he would send an experiment up on a space. Basically, it was an experiment to be conducted in space to test a theory of quantum mechanics. And if I'm not mistaken, wasn't it the many world? Wasn't it the? I think it was this one, or it was basically it was an experiment to be sent into space to test for some crazy theory. I'm pretty sure it was quantum mechanics. We're gonna fact check this for sure and put it in the comments. So I will let you guys know.
What are you talking about? You didn't even explain.
No. Okay. So Stephen Hawking, before he died, right? He released a paper. I don't think he finished it. I think that was the problem, where he was gonna send an experiment to space, and something was gonna happen. That's the part I forgot. But I'm pretty sure it had something to do with quantum mechanics. If I'm wrong, it could have something to do with maybe astrophysics, because he was more of a cosmologist. I don't know why he would have anything to do with quantum mechanics. Cosmology makes more sense. Maybe, but it was some big experiment, and I'm going to fact check it and put it in the comments. because I thought it was the many worlds interpretation, so I could be wrong. Just saying.
Well, that would be cool. I was also going to say something. Oh yeah, one thing, this doesn't really have anything to do with quantum mechanics, but I was on the website for U of T, and so to do, like, I'm in astrophysics, and so to do a master's in astrophysics, it's a master's in science, like an MSc.
Yeah.
But to do a PhD in astrophysics, it's actually a like part of the Department of Philosophy.
Oh, is it?
Yeah, it's something weird like that.
That's interesting. Well, I guess
Yeah.
at one point, and I'm pretty sure there are mandatory philosophical PhD programs, right? That like ethics of physics and stuff that even we have to do in fourth year. I think philosophy is just pretty entangled with physics and just science in general, right? Especially at like high levels where you're basically just questioning reality and existence and stuff like that. You know?
Wait, what does PhD stand for?
Wow, I really know this.
Let me just search it.
No, I know what?
PhD stands for.
No. Oh, Doctor of Philosophy.
Yeah,
Doctor of Philosophy. Doctor of Philosophy. Yes, I knew it. I'm like, no way.
Okay.
And I did not search it up. Oh, there's no way to prove that.
Okay, wait. So never mind. What I said was wrong.
What?
Because no, Doctor of Philosophy. Why is it called that?
That's just the name of that's just a PhD. That's
Yeah,
just
but
what it's called.
why is it called that?
Because that's what I'm saying. I think at that level, everyone pretty much becomes philosophers, bro.
Wait, that's not true. That is not accurate.
I actually don't know why it's called PhD. I actually don't. Oh, see. The Doctor of Philosophy degree, which is a misleading moniker because most philosophers, this term is increasingly popular degree derives from the original meaning philosophy. Yeah, that's just how it started, low-key. I don't think it's
No, it's because philosophy means love of wisdom.
Oh, Greek word philosophy, I mean love of wisdom.
Yeah. So
Yes,
when you're doing a Doctor of Philosophy, it's like you're going into your field. You're going into your field with
Yes, sir.
loving wisdom.
Also, yeah, PhD in astrophysics doesn't really exist. You would have to do a PhD in something very specific. Like, you can't do a PhD in, astrophysics. That's very general.
Oh, yeah, that might be right.
That stuff. You can't get PhD physics. That's not how it works. You need to get a specific thing. That's the entire point, right? Like, as you advance, undergrad, grad, PhD, you get more specialized. So.
Yeah, you know what's crazy? I can actually apply for a PhD right
after undergrad, yeah. Because
undergrad.
Nowadays, a lot of universities don't require masters because a lot of people are just like, it's an extra waste of time. Because a lot of universities include the first 2 years of masters into, I think, the first year of PhD or something like that.
That's crazy.
It's kind of covered already. So they anyways do it, so why not?
Yeah, that's pretty crazy. Anyways, going back to...
going back to the podcast.
Quantum mechanics / parallel universes. Have you seen Rick and Morty?
Oh, of course.
You know that one episode, the interdimensional cable?
Yeah.
Yeah, that one actually, it's a very good example of parallel universes. Because, every time they change the channel, they see a commercial in a different universe. And it gives you kind of a taste of what, you need to understand that literally everything is possible when it comes to parallel universes. So, I mean, they do it in a comical way where,
obviously, because it's just it's a show at the end of the day.
Yeah, it's just funny bits. But they actually, they get the idea right.
Yeah.
Where the universe can be similar to theirs and it can have, English speaking beings and, they have TV and stuff like that. But just a couple of things are different and some things are off and, they make it funny, which is, I really recommend watching
Rick and Morty.
If you're into
if
science and stuff, it's actually it's funny and it's actually
but it's a sense of humor in itself. You kind of have to appreciate the sense of humor. It's kind of like The Office, some people just won't like it because they're just like, no. You
Yeah,
know?
that's weird. That's weird though. Like
No, but I
everyone
have
has to
had
watch The
people who are
Office.
just like, I hate The Office because it's just terrible humor. And I mean, I just sit there with my jaw dropped, but, you know, some people just, that's just them. Can't do anything about it.
Wait, have you seen? No, you haven't seen the whole Office.
I haven't seen the
right?
whole Office, no. I've only seen like the first 2-3 seasons.
That's a big strike. You
That's
need
a
to
big
watch the whole
strike, yeah.
thing.
That's a big strike.
Yeah.
Also, talking about parallel universes, one thing I think we mentioned, I don't know, but the entire point is that we should not be able to, you know, communicate with other parallel universes. But in Rick and Morty, they do. Right?
Do they?
Don't they? Of course.
I don't.
They
I
keep,
don't think so.
I mean, they
Different
can,
universes.
okay, anyways, forget Rick and Morty. That's not the point. The point isn't Rick and Morty. The point is that between parallel universes, the entire thing with Schrodinger's cat, as I said, you wouldn't even know that there's another version of you that is alive. So because of that, you wouldn't be able to ever truly get into your life in a parallel universe because, as I said, it's just different universes, right? But wouldn't it be cool if you could? I think we can talk about that for a bit. What would you do if you could enter a parallel universe where you made a different choice? You know?
Mhm.
Like, I think that would be a cool question.
Yeah,
Like-
I mean that also requires inter-universal travel.
Yeah, I mean, of course. Assuming that is all possible.
But wait, something that we could actually talk about is
Yeah.
the grandfather paradox.
Oh,
which,
yeah, but this is more to do with time than to do with, like, parallel universe. But you know what? Why not? Let's go for it. We can now talk a little
Yeah.
bit about timelines, too. This is going to be
Yeah,
crazy.
I mean, yeah, timelines do have a role in what we're talking about.
Absolutely.
So, the grandfather paradox,
Mhm.
very common.
Hmm.
You know, people know this from not even the physics world because, I mean, it doesn't really have much to do with physics, but it's still cool to talk about. So, if you can go back in time and kill your grandfather, would you die? Would you not even be born to be able to go back and kill your
Mhm.
grandfather? Would, you know, ...
Hmm. Yeah, because
Yeah.
the big question or like the big thing is if you go back and kill your grandfather, then your grandfather was never born, which means you were never born, which means you can't go back and kill your grandfather, which means he should never not be dead. But that means if he's not dead, that means you're born. That means you should kill your grandfather. So it's a whole big paradox. Hence the paradox.
So a lot of people would just kind of, they'd be like, no, well, I guess time travel or traveling back in time is just impossible because
Mhm.
of that reason.
Hmm. But yeah.
Yeah, go ahead.
Okay, so but right now this is the big thing. There was a video put out by Minute Physics. I'm not gonna lie. I'm not gonna take credit for this because that is where I learned that this paradox can basically be broken in a way where when you go back in time. Now, first of all, going back in time in itself is, as Parker was saying, pretty much impossible. But assuming that it's fine, let's say we do go back in time, somehow kill our grandfather. The moment that happens, the second we pull the trigger and he dies, what physics and math, what that would state to avoid the paradox is that a universe would be created or a timeline would be created. And again, you wouldn't know that this timeline is being created. You wouldn't even know how to get back to your original timeline.
Actually, I think that's false.
What?
I don't think it's when you kill your grandfather. I think it's just the moment you go back in time, a new timeline gets created. Because what if
Well,
you
technically, if you just go back in time, well, yeah, okay, yeah, a new timeline is created with the same future events, technically. If you just go back in the past and don't do anything, another
Yeah.
timeline is created with the exact same future events, and nothing happens.
Well, not,
I mean,
not
nothing-
exactly because that would imply that you could be born twice on the same timeline.
Yeah, but again, this is all assuming that going back in time is possible, right? Because that entire assumption in itself is false. But the only way to explain the grandfather paradox is to assume that time travel is possible. So that's what I'm doing. I'm just assuming that it's okay that we're back in the past. So what will happen if we kill our grandfather? So I'm saying that if we do kill our grandfather, we will still live because we will be living in a different timeline, right?
All right.
Is basically the point I'm trying to get at. And if I'm not mistaken, I'm pretty sure there's even if we go back, and then after killing our grandfather, if we go into the future somehow, again, somehow, very theoretically, we won't be able to go to our future that was our future before we went to the past. You know, it'll be a completely different future, and we can't do anything about it unless we go even further back into time and undo what we did the previous time. That's a possibility. So this is where time travel gets all confusing.
Yeah, and that's why I honestly, I don't think time travel back in time is physically possible. But as we talked about in our special relativity episode, which a part 2 is going to be coming soon, by the way, as we talked about in special relativity, time travel forward is possible.
Very much so.
And also time, like relative time travel backwards is also possible, because you know the twin paradox.
Yeah, like one is traveling. One of them, very much possible. Yeah.
So technically,
because one is traveling faster, one is traveling slower, obviously.
Yeah. So when the other one comes back, lands on the Earth, he technically he landed in the future.
Yeah.
Right.
Yeah. Yeah.
Far in the future. But technically, he's landing relative to the Earth. He's landing in the past. So, like, if you were the other twin that was old, and your young twin comes back to the Earth, he's in the past. So technically, he traveled back in time.
No, he
relative
did. Wait,
to you.
1 minute.
Yeah, he's younger than you. He traveled back in time relative to you.
Oh, relative to you. Yes. Sorry. Continue. No, you said relative to the Earth. Relative to you.
Well, yeah, relative to the Earth, he is younger.
No, relative to you, he is younger. Relative to the Earth, he's fat. He's fine.
Relative to everyone on the Earth.
Like people.
Your time dilation has to do with your velocity.
Yes.
If you're going away from a person, you're going away from the Earth at the same rate.
Yes.
So, with respect to the Earth, you're going to be younger than everyone there.
You're going to be younger, but you're technically... Okay, I guess... Okay, but the way you said it, you implied that you're going in the past, the way you said it. Like, I just didn't catch on the way you said it.
You're not going to be younger in age, but you're going to be younger in the sense that...
Yeah. You're
supposed to be older.
You're going to be younger than everyone else there. That makes sense. Like that.
That was like that was everyone else that was born the same year as you.
Exactly. Yes,
there you go.
That's exactly. What I thought you said is that when you go and come back, you return before you left. Like you get back in the past. That's why I'm like, what? That doesn't make any sense.
No, it's just relative to
that makes a lot more sense. That makes a lot more sense. So Stephen Hawking basically made this theory called the chronology protection conjecture, which I think I have mentioned before, now that I'm mentioning it. But basically this states that you can't go back in time. And obviously it's pretty obvious that you can't go back in time, and you shouldn't even be able to.
Obviously, it's pretty obvious.
Sorry, I should have worded it differently. But what I'm trying to say is the best analogy to think of time. I think this was in, you can think of the arrow of time as one, right? The famous Stephen Hawking arrow of time. But a more, like one that I like more, to be honest, and this one I'll explain, is the river, right? Like it's a flowing river that always keeps flowing in one direction. You can never, like any spot on the river, wherever you are on the water, you keep moving forward. No way to get back. Absolutely no way to get back. So that's basically the best analogy that I can give when you talk about time itself. Because space-time just can't be broken, especially when you're going backwards. So, timelines. Timelines are really cool.
That is correct.
Timelines are really cool things to talk about. Also, timelines are so, like, they're so common in sci-fi shows that they're misrepresented so many times that sometimes they just don't make any sense. Like they go in the past, completely mess things up, but somehow the future is still intact. And there are some shows like that just completely don't worry about the timeline whatsoever. But timelines are really cool and important.
I mean, it's hard to get it right and make it interesting at the same time.
That's true.
Anyways,
that's true as well.
We are pulling up pretty late into the podcast, so this
Yeah.
is a good moment to let everybody know that they should subscribe / follow
Absolutely.
wherever you're listening. It could be Spotify, it could be Apple. If you're listening anywhere where they let you comment, make sure to comment something. If you want us to talk about something, if you have a question that we can answer, we will definitely do that. And oh yeah, we did get a comment on episode 21.
Oh, yes, of course. So on episode 21, sorry, I don't have the comment section pulled up, but someone asked me if I spoke Hindi, and yes, I do. Well, I understand it very well. Don't speak it too well, but I do understand it. So that hopefully answers your question. And I did want to say one thing before we end the podcast. This particular one, Parallel Universes, was actually suggested by a friend of mine while we were climbing a building. Interestingly enough, we were climbing a building, and I was like, we were just talking about universes, and then he's like, why don't you do a podcast on parallel universes? And I said, that is such a great idea. And then here we are. I just thought I had to share that with everyone listening.
That
So
is
thank you.
awesome.
Thank you.
So yeah, thank you everybody for listening.
Mm-hmm.
This has been the Math and Physics Podcast with your host Parker.
And I am Ray, and we will see you soon.
Okay, see ya.